for machine design. I'm David DeFrancis. We are also with me Matthew Renda and Tyler Watson. So the objective of this project is to design a machine capable of transferring industrial rolls of paper from a manufacturing line to a forklift. This system must rotate 90 degrees during the transfer process, and our design will focus on the selection of and analysis of gears, bearings, and lead screws.
We broke this down into a list of design specifications. So we would need to transfer 30 rolls per hour for 2 8-hour shifts during a day. We'd have 40 seconds to transfer the roll. So to accomplish that 90-degree cradle rotation that we need, it would be 40 seconds. We had a steel cradle structure which would support our paper roll, and then that entire rotational structure would be supported by 2 bearings. And then to power the system, there would be a gear train which is actuated by a lead screw, which is powered by an electric motor.
So, general overview here of the entire machine. The motor at the bottom is going to be powering the power screw, and then the power screw powers gear 2, and then gear 2 meshes with gear 3, getting the shaft to rotate 90 degrees, and the pillow blocks and the bearings are supporting the shaft.
So for the gear analysis, we'll start with the free body diagrams here, as they can be seen on the right. And we'll be focusing mainly on the torque resisting the motion from shaft A that is induced by the weight of the roll and the cradle system, and then the force between gear 2 and 3. Also in the free body diagram, we have the force of gear 3 on shaft B and the force of gear 2 on shaft A. And the assumptions we will be making are that the gear teeth have an involute profile and a pressure angle of 20 degrees. So, to find the forces in the gears, it is necessary to have the maximum torque generated from the roll and the cradle. And the cradle system has a total weight of about 9,000 newtons and gives a torque of about 3,600 newton meters. And after dividing the position of the motor relative to shaft B, the next step is to find an optimal gear ratio, sweep angle, and radius for gear 3. The gear ratio we came out to be is 4/3, with the gear on the cradle being the larger gear, and the sweep angle of 120 degrees, which is also the degree of rotation from gear 2. And the final force between gear 2 and 3 is about 23,000 newtons. And on the right, we can see the graph of gear force versus the input radius for an optimal radius size of gear 3. For the torque and force calculations, the force between two gears is based on the output torque, radius, and the pressure angle. And given the numbers we previously stated, this is how we find our torque. And in the code here, you can see how we found it. And based on the values, you can also find the input torque needed from the crank arm and the motor assembly. After getting all the specifications for the gears, we have gear 2 has 63 teeth, a diameter of 252 millimeters, modulo of 4 millimeters, and the material is a 1045 carbon steel with a yield stress of 310 megapascals, and it's estimated to cost $1,000, and this was found on rushgears.com. Also found on rushgears.com is gear 3, which has 84 teeth, a diameter of 336 millimeters, the same module as gear 2, along with the same material and yield stress as gear 2, and although the cost estimate is slightly larger at $1,250. Testing the failure of the gears, having the force of the gear gear 2 onto 3 is as the 23,000 newtons. The stress and factor of safety for gear 2 is 79.26 megapascals and a factor of safety of 3.91, and gear 3 has a maximum stress of 76.63 megapascals and a factor of safety of 4.04.
Once we had the torque requirement known from our gear ratio and the load at the cradle, we were able to set up a free body diagram which would illustrate how the force required from the power screw would change throughout the cradle's rotation. So we had a characteristic equation which is pretty much defined in terms of 2 different variables, phi, which is the angle of the motor or the lead screw, and theta, which is the angular position of the crank arm. We generated 2 quick plots that would kind of help to illustrate how this movement occurs. On the left is the X and Y position of the crank arm, which is as expected a symmetric U as we go throughout our 120 degrees of travel. A kind of curious conclusion of this is that our phi angle is not symmetric, and you see a much steeper increase towards the end of the travel versus the start. To validate this, we created a pretty basic CAD model, which would kind of show or illustrate this concept. So because our angular travel is between 30 and 150 degrees, we went 10 degrees from the start and the end of travel, and we saw a very large difference in phi values, which corresponded to the graph. So that validated our asymmetric phi kind of assumptions and calculations. Because with the asymmetric phi validated, we now had both theta and phi, which are the two variables we needed to find the force from the power screw throughout different points of the rotation. And we calculated this using a MATLAB script, which would sweep through every angular theta value. And then we found the maximum force from this graph, and we used that as the requirement for what our power screw must be able to hit. That led us to a power screw force requirement of 5,400 newtons and a linear velocity of 36 millimeters per second, and that also meant that our screw must be self-locking. We also checked against various different kinds of thread failure mechanisms, such as torsional stress, tangential shear stress, axial stress, first thread bearing stress, and thread root bending stress. So we took all these different stress or different failure mechanisms and put them into von Mises stress, essentially saying they're all occurring at once. That led us to a von Mises stress of only 43 megapascals, which is a factor of safety of 3.36 against our 2100 psi yield strength. That led us to our selected power screw from McMaster of a 6624K8, which is a M20 ball screw with a lead of 10 millimeters. In order to hit the requirements of the torque to drive the load and for the linear travel of the motor, we had to spec a speed and torque requirement for the motor. The motor must be able to drive 26.2 newton meters worth of load, and the torque to lower load was calculated at 7.3, which validates that the screw is self-locking. To hit our linear travel requirement, the motor must be able to rotate at 220 revolutions per minute. This leads to a motor power required of 603 watts. If we wanted to put a factor of safety on the torque that the motor could supply, or both the torque and the speed, we just have to scale that power requirement accordingly.
All right, so before we can start the bearing analysis, what we're looking for here is the reaction forces at each bearing. In order to find, or once we find the reaction forces at each bearing, then we can actually go and spec a bearing. So, in order to get these reaction forces, we're going to need to know weights of the vertical beams and the horizontal beam of the cradle, and also the paper load. So you can see here, the weights are then turned into point loads, and then turned into force couples, and then you just have one resulting couple and 3 loads on the shaft from the beams. Okay, so then you have your 3 forces, and you have our free body diagram in the top right is an isometric view of everything here. Then we can look at the YX and the XZ free body diagram, and basically some forces, some moments, and then we can end up finding our reaction forces since we have all the other values. So now that we have our reaction forces, we can go ahead and find the equivalent force. And so basically, there's no axial force as well. That's 0. There's nothing pointing in the axial direction, only the radial direction. And so then we find our radial force by squaring both reaction forces, the RAY and the RAZ. And so then, once we have our equivalent force, we can then find our dynamic load rating, which is what we need to go and spec our bearing from the equation shown. And for more specifics on this, you can look at the code. But basically, to find the lifetime, we can look at the general overview of what we had before, which is 16 hours a day, 5 days a week, 15 weeks a year, and 10 years to find our lifetime. And yes, and then our max dynamic load rating was 118 newtons. So then, with that information, we can then go and find our bearing and our pillow block. So this deep groove bearing is from Misumi, and it supports our required load rating. And then also, I forgot to mention before, but we have FE, which is our equivalent force, is multiplied by 2 to factor in our factor of safety. So, we have this bearing, and we have the pillow block from Misumi, and the total cost of this would be $397. So then the total cost of our machine overall, you can see here from all of our components, is $2,950.58.